Hello friends, I welcome you in lecture number 3 on higher order ODEs. In lecture number 2 we have seen how to solve second order homogeneous equations. Today we will generalize that concept to linear ordinary differential equations of any order, and of course we are considering homogeneous linear ordinary differential equations. So we are going to generalize the method from second order homogeneous equations to equations of order greater than 3. So we start with nth order homogeneous linear differential equation. So this is the standard form of nth order linear homogeneous differential equation. The first term is nth derivative of y plus a1 times n minus 1th derivative of y plus a2 times n minus 2th derivative of y, and so on. Here last term is an into y equal to 0, and here a1, a2, an are constants. Now method is same. First we will replace nth derivative of y by lambda raised to n, and y will be replaced by 1 in this equation number 1, so that we will obtain auxiliary equation of this equation number 1. So as we know, to write down auxiliary equation, we will remember this nth derivative of y is replaced by nth power of lambda. So if we replace this nth derivatives by powers of lambda, this is going to be lambda raised to n plus a1 times n minus 1th derivative of y is replaced by lambda raised to n minus 1. Similarly, this is replaced by lambda raised to n minus 2, and so on. First derivative of y is replaced by lambda, and this y is replaced by 1. So this is the auxiliary equation of this equation 1. Now this is nth degree polynomial equation in variable lambda, and we know that this nth degree polynomial equation will always have n roots. So there are n values of lambda which satisfy this equation number 2. So we assume that these n roots are lambda 1, lambda 2 and lambda n. Now for these n roots there are different possibilities. One possibility is all the roots may be real and distinct. Another possibility is some roots are equal, some roots are not equal and real. Another possibility is some of the roots are real and other roots are complex. Another possibility is some of the real roots are repeated, some of the real roots are non-repeated, and remaining roots are complex. So there are several possibilities. So depending on the nature of roots of auxiliary equation, we will write down the general solution. So here we are considering 3 or 4 possibilities, but there are not only 3 or 4 possibilities. Depending upon the order and nature of roots of given roots of auxiliary equation, there will be different possibilities, and that will vary from equation to equation. But for understanding, we are considering several possibilities in this lecture. So first possibility we are considering is, suppose all the roots are real and distinct, or all the roots are real and different. So in this case the general solution is given by y equal to c1 times e raised to lambda 1x plus c2 times e raised to lambda 2x, and so on, cn times e raised to lambda nx. Suppose we have third order differential equation, and if all the roots are different, then we will have c1 times e raised to lambda 1x plus c2 times e raised to lambda 2x plus c3 times e raised to lambda 3x. This will be the general solution if order of equation is 3 and all the roots are different. Suppose order of equation is 4 and all the roots are different, then we will add c4 times e raised to lambda 4x. So it is similar to the case of second order equation. In second order equations we are having 2 arbitrary constants, and in nth order differential equation we must have n arbitrary constants. So if all the roots are different, we will write down terms of the general solution in this way: c times e raised to lambda x. So we will put lambda equal to lambda 1, lambda 2, lambda n, and c1, c2 and cn. So this is the general solution in the case all the roots are real and distinct. So we have considered one example here. Solve this differential equation: y triple dash minus 2y double dash minus y dash plus 2y equal to 0. So first we write down the auxiliary equation. This is replaced by lambda raised to 3 minus 2 times second order derivative is replaced by second power of lambda, first order derivative is replaced by lambda, and this y is replaced by 1, so last term is plus 2. So this is easy to factorize. Here we can take lambda square common, here we can take minus 1 common. So lambda square times lambda minus 2, and if we take minus 1 common here, we will have lambda minus 2 in the bracket. Now we consider lambda minus 2 common, and we have lambda minus 2 times lambda square minus 1 equal to 0. Lambda square minus 1 is replaced by lambda minus 1 into lambda plus 1. So three possibilities are lambda minus 2 equal to 0, lambda minus 1 equal to 0, and lambda plus 1 equal to 0. Therefore lambda equal to 2, lambda equal to 1, and lambda equal to minus 1. So all the roots are real and distinct. So therefore the general solution is y equal to c1 e raised to 2 into x plus c2 e raised to 1 into x plus c3 e raised to minus 1 into x. And here this c1, c2, c3 are arbitrary constants. Arbitrary means we can take any value for them. So we should mention that c1, c2, c3 are arbitrary constants. So in this way we can easily find out solution of homogeneous linear ordinary differential equations with constant coefficients. So first we have to write down the auxiliary equation, then we find the solution of auxiliary equation, and depending upon the nature of roots we have to write the appropriate general solution. Second possibility is, suppose some roots are repeated. Suppose first k roots are equal. Suppose lambda 1 is equal to lambda 2 is equal to lambda 3 equal to lambda k, and remaining roots, say lambda k plus 1, lambda k plus 2 and lambda n, are distinct. So all the roots are real, first k roots are equal, and remaining roots are distinct. So in this case, if we write as in case 1, then our solution will look like this: c1 e raised to lambda 1x, c2 e raised to lambda 2x, c3 e raised to lambda 3x, ck e raised to lambda kx plus ck plus 1 e raised to lambda k plus 1 times x plus ck plus 2 e raised to lambda k plus 2 times x, and so on, cn e raised to lambda nx. But first k roots are equal, so we can consider lambda 2 equal to lambda 1, lambda 3 equal to lambda 1, and so on, lambda k equal to lambda 1. So here I replace lambda 2 to lambda k by lambda 1. So we are writing as in the first case. Now what happens if we consider these first k terms? Then e raised to lambda 1 x is common in every term. So if we take e raised to lambda 1 x common, we will have c1 plus c2 plus ck times e raised to lambda 1 x, and this is going to be new constant, say c dash times e raised to lambda 1 x. So up to this e raised ck, we have only one essential constant. So there will be less than n essential constants in the general solution if we write in this way. So why this happens? Because we are having same function in each term up to kth root. So to sort out this problem, we will be multiplying by powers of x. So here, to make these two different, we multiply with x. Similarly, to make these two different, we multiply by x square here, and so on. We keep on multiplying by powers of x. So if I have c3, I have to multiply with x square. In the next term, I will write c4 x cube e raised to lambda 1x. So here I have to multiply with x raised to k minus 1, because I am having ck here. If I have c2, I multiply with x, that is 2 minus 1. If I have c3, I multiply with x square, 2 means 3 minus 1. So if I have ck, I will write x raised to k minus 1, so that I will have n essential constants. So if roots are repeated, we will be keep on multiplying by powers of x, so that we have total n essential constants in the general solution. So in this case, if k roots are equal, first k roots are equal and remaining roots are different, then general solution will be in this form: y equal to c1 e raised to lambda 1x, c2 times x e raised to lambda 1x, c3 times x square e raised to lambda 1x, ck times x raised to k minus 1 e raised to lambda 1x, and remaining roots are different. So ck plus 1 e raised to lambda k plus 1 times x, ck plus 2 e raised to lambda suffix k plus 2 times x, and so on, cn e raised to lambda nx. So in short, if we have repeated roots, then we will be multiplying by nth power of x, so that we have required number of essential constants in the general solution. So we understand with the help of example. Solve the following differential equation: y triple dash minus 2y double dash minus y dash plus 2y equal to 0. So this is third order homogeneous linear differential equation. First we write its auxiliary equation. So auxiliary equation is y triple dash is replaced by lambda cube, y double dash is replaced by lambda square, y dash is replaced by lambda, y is replaced by 2. So here we can take lambda square common. So we have lambda minus 2 here, minus 1, and this is lambda minus 2 equal to 0. So I think we have discussed this here. I am having this same equation here: y lambda cube minus 2 lambda square minus lambda plus 2 equal to 0. So that is the case of distinct roots. We consider another problem. Fifth derivative of y minus 3 times fourth derivative of y plus 3 times y triple dash minus y double dash equal to 0. So we first write down the auxiliary equation. Auxiliary equation here is fifth derivative of y is replaced by lambda raised to 5 minus 3 times fourth derivative of y is replaced by lambda raised to 4. Third derivative is replaced by lambda raised to 3 minus second derivative is replaced by lambda square equal to 0. Now there is lambda square in every term, so we can take lambda square common. So here we will be having lambda cube. This is going to be minus 3 lambda square plus 3 lambda minus 1 equal to 0. Now if we observe, this is nothing but cube of lambda minus 1. Okay, if you use this formula with a equal to lambda and b equal to 1, you will have minus 3ab a minus b. So if we use this formula with a equal to lambda, b equal to 1, we will have lambda cube minus 1 minus 3 lambda times lambda minus 1. So this is going to be lambda cube minus 1 minus 3 lambda square plus 3 lambda. Lambda cube minus 3 lambda square plus 3 lambda minus 1. So this we replace by cube of lambda minus 1. So that means lambda square equal to 0 and lambda minus 1 cube equal to 0. So therefore lambda is 0. 0 is repeated 2 times and lambda equal to 1. This is repeated 3 times. This is repeated 2 times. So this is the case of equal roots and real also. So therefore the general solution is y equal to, first we write for 0. So 0 is repeated 2 times. So we can write c1 e raised to 0 x plus c2 e raised to 0 x. But here this is repeated. So here we multiply with x. Similarly we write for lambda equal to 1. c3 e raised to 1 into x, that is e raised to x plus c4 e raised to x plus c5 e raised to x. So here this is also repeated. So here we multiply by x and here we multiply by x square. And this we can rewrite as e raised to 0 x is 1. So we have c1 plus c2 x, and here if we wish we can take e raised to x common. So we have c3 plus c4 x plus c5 x square times e raised to x, and here c1 c2 up to c5 are arbitrary constants. c1 c2 c3 c4 c5 are arbitrary constants. So this is the general solution in the case of repeated roots. So we should take care of these things. If these two are equal, to make them different we have multiplied by x. Similarly here e raised to x is repeated 3 times, so we keep on multiplying up to second power of x. Now we consider another possibility of complex roots. Suppose we have two complex roots, lambda 1 equal to alpha plus I beta, lambda 2 equal to alpha minus I beta, and remaining roots are real and distinct. As we know, complex roots always occur in pair and they are conjugates of each other. So here one root is alpha plus I beta, so we must have its conjugate as second root. So the part of general solution corresponding to complex roots is c1 e raised to alpha x cos beta x plus c2 e raised to alpha x sin beta x. This we have discussed in previous lecture. And remaining roots are real and distinct. So the part of general solution corresponding to these roots is c3 e raised to lambda 3x plus c4 e raised to lambda 4x and so on, cn e raised to lambda nx. Now suppose we have repeated complex pairs. So suppose one pair is lambda 1 equal to alpha plus I beta, lambda 2 is alpha minus I beta, and we are having repetition of this pair. So suppose lambda 3 is also alpha plus I beta and lambda 4 is also alpha minus I beta. So here this complex pair is repeated, alpha plus or minus I beta is repeated. So we are having 4 complex roots, alpha plus I beta is repeated, similarly alpha minus I beta is repeated, and remaining roots are real and distinct. So in this case, how to write down the general solution? So corresponding to first pair, this is the part of general solution corresponding to first pair, e raised to alpha x cos beta x plus e raised to alpha x sin beta x. Now for this pair also we have to write these functions, e raised to alpha x cos beta x, e raised to alpha x sin beta x, but they will be repeated. So to make them different we have multiplied by x. So this is the part of general solution corresponding to second complex pair, alpha plus or minus I beta. So e raised to alpha x cos beta x is there here also, e raised to alpha x cos beta x. So to make them different, here we have multiplied by x. Similarly here also e raised to alpha x sin beta x is repeated, so we multiply by x, and remaining roots are different. So we have c5 e raised to lambda 5x, c6 e raised to lambda 6x, and cn e raised to lambda nx. So these are the different possibilities. There might be another possibilities also, but we know how to write down the general solution now. After discussing this much of possibilities, what we should take care is, if roots are repeated, we have to multiply by powers of x to make them independent. And in the case of real roots, function we are using is e raised to lambda into x, and in the case of complex roots we are using e raised to alpha x cos beta x, e raised to alpha x sin beta x. So we consider one problem here. Solve the differential equation, fourth derivative of y plus 4 times y equal to 0. First we write down the auxiliary equation. Auxiliary equation is, here fourth derivative will be replaced by lambda raised to 4 plus 4 times y will be replaced by 1 equal to 0. Now how to factorize this? So we can see these two are perfect squares. So we can find out the middle term for this using this formula. Middle term square equal to 4 times first term into last term. So if we consider this as first term, this as last term, then we have 4 times lambda raised to 4 into 4, that is 16 lambda raised to 4. This is square of middle term. So middle term equal to plus or minus 4 times lambda square. So we can set either 4 lambda square or minus 4 lambda square as middle term, but here I am considering plus 4 lambda square, and because I am adding 4 lambda square, I have to subtract 4 lambda square. I am not taking negative 4 lambda square here because that is not useful. If we consider negative 4 lambda square, then we cannot factorize further. So we consider 4 lambda square as middle term. Now if we observe, this is square of lambda square plus 2. If you expand this, this is going to be lambda raised to 4 plus 2 into 2 lambda square, that is 4 lambda square plus 4, and this we can rewrite as square of 2 lambda. So 4 lambda square can be written as square of 2 lambda, that is going to be 2 lambda square is 4 lambda square. Okay, fine. Now we use the formula of a square minus b square with a equal to lambda square plus 2 and b equal to 2 lambda. So first we write a minus b, that is lambda square plus 2 minus 2 lambda, and then we consider a plus b, that is lambda square plus 2 lambda equal to 0. So here a minus b and a plus b equal to 0. So therefore lambda square minus 2 lambda plus 2 equal to 0, lambda square plus 2 lambda plus 2 equal to 0. So now we can find out solution of these two quadratic equations using the formula. So here if we compare with a lambda square plus b lambda plus c equal to 0, we have a equal to 1, b equal to minus 2 and c equal to 2. So the formula is minus b, that is minus of minus 2 plus or minus b square, that is square of minus 2 minus 4 into a into c equal to 2, a equal to 1 divided by 2 times a. Therefore lambda equal to 2 plus or minus square root of 4 minus 8 divided by 2. Therefore lambda equal to 2 times plus or minus square root of minus 4 over 2. Therefore lambda equal to 2 plus or minus square root of 4 is 2, and here we have minus 1 divided by 2. So therefore 2 will cancel out, 1 plus or minus square root of minus 1, that we replace by I square. So therefore lambda equal to 1 plus or minus I. So this is one possible pair of complex roots. Now we solve another quadratic equation using the same process. For this equation a is 1, b equal to 2 and c equal to 2. So here lambda equal to minus b means minus 2 plus or minus b square means 4 minus 4 into a into c, so that we write directly now, divided by 2 into a. This is going to be minus 2 plus or minus minus 4 over 2. So here minus 2 plus or minus square root of 4 is 2 and under root of minus 1 divided by 2. So 2 will cancel out and we have minus 1 plus or minus under root of minus 1 is replaced by I square. So therefore lambda equal to minus 1 plus or minus I. So this is another possible complex root, and we have different complex roots. Lambda equal to 1 plus or minus I, lambda equal to minus 1 plus or minus I, and our equation is of fourth order. So we have 4 complex roots or 2 complex pairs. One is lambda equal to 1 plus or minus I, lambda equal to minus 1 plus or minus I. So lambda equal to 1 plus I, 1 minus I, minus 1 plus I, and minus 1 minus I. These are the roots of auxiliary equation. So there are 4 complex roots and all are different. So therefore the general solution is y equal to, first we write down corresponding to this. So for this pair alpha is 1, beta is 1. So we have c1 e raised to x, e raised to alpha x, alpha is 1. Cos beta x, beta is also 1. So we have c1 e raised to x cos x plus c2 e raised to x sin x. So this is the part corresponding to this first pair. Similarly for this pair alpha is minus 1 and beta is 1. So c1 and c2 are used. E raised to alpha, that is minus 1x cos beta x, that is beta is 1, plus c4 e raised to minus x sin x, and c1 to c4 are arbitrary constants. So in this way we can use this method to find out solution of homogeneous linear equations. Suppose my roots were lambda equal to say 2 plus or minus 3i, or we can write separately. Suppose our roots of auxiliary equation are lambda equal to, lambda 1 is 2 plus 3i, lambda 2 is 2 minus 3i, lambda 3 is also repeated 2 plus 3i, and lambda 4 is also repeated 2 minus 3i. Suppose these are the roots of auxiliary equation of some fourth order differential equation. So for this type of roots general solution will be, first we write for this pair. For this pair alpha is 2, beta is 3. So we have c1 e raised to 2x cos 3x plus c2 e raised to 2x sin 3x. and now this pair is repeated. So for repetition, again we write e raised to 2x cos 3x plus c for e raised to 2x sin 3x. So now we can see these two are same, so to make them different, here we multiply by x, so this becomes independent. Similarly here also this is repeated, so we multiply by x. So if we have repeated roots, then we will be multiplying by powers of x, so that our functions become independent. So I have not discussed this case, so therefore I explain using these roots. So in this way, depending on the nature of given differential equation, we can write general solution easily. So in the upcoming lectures, we will be doing some more problems of this type, so that you may have clear idea about writing the general solution of homogeneous linear differential equations. So this is all about this lecture. I hope you like it. Thank you very much.